principle of the gas turbine engine is basically the same as that of the piston engine propeller combination. They both propel a mass of air backwards. Mass times acceleration equals force. In a gas turbine engine, the mass, m, mentioned in the equation, is the air delivered by the compressor. The acceleration in the equation is the difference in the outlet velocity of the air, VO, to that of its inlet velocity, V1, due to the addition of heat energy. Force equals mass times V0 minus V1, which equals thrust. With the piston engine propeller combination, the propeller drives a relatively large mass of air backwards fairly slowly, while the gas turbine throws a small mass of air backwards relatively quickly, and the velocity change imparted to it. The working cycle of the gas turbine engine is called the Brayton cycle, after George Brayton, an American mechanical engineer who invented the continuous ignition engine, which was the basis of the gas turbine engine. The Brayton cycle and the working cycle of the four-stroke piston engine, the Otto cycle, are very similar, as can be seen in this diagram. The induction, compression, the pressure volume diagram shown here, otherwise known as the Brayton cycle, represents the working cycle of the gas turbine engine in its simplest form. Air at atmospheric pressure enters the engine at point A. As we previously stated, theoretically combustion in the gas turbine engine occurs at a constant pressure. This is achieved partly through the continuous process of the Brayton cycle, and also by the fact that the combustion chamber is not an enclosed space. These circumstances ensure that there are no fluctuations of pressure in the engine as there are in the piston engine, where the turbojet is a heat engine. The higher the temperature attained in combustion, the greater the expansion of the gases, and hence gases behave differently from the other two commonly studied states of matter, solids and liquids. So we have different methods for treating gases and understanding how they behave under certain conditions. Gases, unlike solids and liquids, because of the interest in hot air balloons in the early 1800s in France, Jacques Charles and Joseph. Although both Boyle's law and Charles' law work in theory, we are unable, with existing technology, to make them work in practice. For instance, as the air passes through the engine, various adjustments must be made to its velocity and pressure. For example, throughout the compression stage, the air must be compressed, but no appreciable increase in its velocity can be easily tolerated. When a compressor and turbine are joined on one shaft, the unit is called a spool. This diagram shows a single spool axial flow compressor turbojet engine. This type of engine was for a long time considered to be the most useful, where an engine with a small frontal area was required, such as this diagram illustrates both a centrifugal compressor turboprop engine and an axial flow compressor turboprop engine. The output from a turboprop engine, the turboshaft engine, can be thought of as a turboprop engine, where the propeller has been. The bypass ratio of an engine is defined as the ratio of the amount of air which is bypassed around the hot core of the engine to the amount of air which passes through the hot core. The experience which was gained by manufacturing and operating the low bypass ratio type of engine, we previously explained that thrust is the product of mass times acceleration. It can be demonstrated that the same amount of thrust can be provided either by imparting a low acceleration to a large mass of air, or by giving a small mass of air a large acceleration. In practice, the former is preferred, since it's been found that the losses due to turbulence are much lower and the propulsive efficiency is higher. In this graph, the levels of propulsive efficiency for several different types of gas turbine engine will be shown. The use of larger and larger aircraft has meant that more passengers can be accommodated in each flight. Thus, air travel has become less and less expensive for the individual. This concept of using large aircraft works well, as long as the aircraft themselves remain serviceable. If, however, one restricting component, such as an engine, becomes unserviceable on a large aircraft, then the expense involved